In this lab, we're going to look at how to represent various compounds. Now, in the lecture, we've looked at two types of bonding. We've looked at ionic bonding, where we combine metals and nonmetals to make compounds, and we've looked at covalent bonding, where we combine nonmetals to make compounds. Now, in this lab, we're going to practice how to represent various compounds, whether in the case of nomenclature, that is converting between names and formulas for these compounds, to a section on covalent compounds where we're going to draw diagrams of these compounds, known as Lewis structures. All right, so we'll get into that in a little bit. All right, so basically what I'm doing here is I'm going to go through the lab report itself and just do a couple of examples from each section just to give you a feel for how we should approach these problems and how you can go about solving them. All right, so in this first section, we're basically looking at how to represent ions, either using their chemical symbols if given the name, or vice versa, how to write out the name of a chemical symbol for an ion. Now, remember, in ionic bonding, we make these ions through a transfer of electrons. Metals like to meet the octet rule by losing what few valence electrons they have to form positive ions, or cations. Nonmetals, which are towards the top right of your periodic table, tend to have a lot of valence electrons already, and so they meet the octet rule by just gaining a few more to become anions, or negative ions. This can seem a little counterintuitive, I think, to students because electrons are negatively charged, so the metals are losing electrons, but they wind up with a positive charge because they're losing something negative. And likewise, our nonmetals wind up having a negative charge because they're gaining negatively charged electrons. So again, kind of weird. They're negative, but it's because they're gaining something. All right. The other thing to keep in mind uh, for naming ions, or just something you should notice, is in the case of these negative ions, these anions, you'll notice an "ide" ending to them. All right, so whenever we have these monoatomic ions, these ions made from one nonmetal, if they have an "ide" ending to them, that should give you a hint that it's a nonmetal you're talking about. Likewise, if you see a negatively charged ion made up of only one element, you know that that's basically a nonmetal, and the name should end with "ide." All right, so yeah, let's try a couple of these out just to get the hang of this. So over here we have calcium, all right, the calcium ion. Notice the lack of an "ide" ending here, so that kind of gives you a hint that we're probably dealing with a metal. It also helps that it ends with IUM. That's a pretty common suffix for metals. So at least that kind of narrows down where you're looking. Not terribly narrows it down because metals make up the bulk of your periodic table. But what does help narrow this down is the fact that there's no Roman numeral here. So if you see a metal that in other words, something that doesn't have that "ide" ending, and there's no Roman numeral, chances are it's a group 1 or group 2 metal. Okay, so that should make looking up the symbol for calcium relatively, at least a little bit easier. Okay, so you look up calcium and you see that it has the symbol Ca. Okay, and now you've got to ask yourself, what charge do I put in the top right corner over here? Okay, I've got to represent my ion as having a charge. Okay, without a charge, it's just calcium metal, and it's not an ion. We need that charge in the top right corner to say what is that atom turned into. So you've got to ask yourself, well, how many electrons does it lose? And to answer that question, you've got to ask yourself, well, how many valence electrons did it have to begin with? So you look at calcium and you see that it's in group 2, which means it had 2 valence electrons. So when it loses those 2 electrons, it winds up having a positive 2 charge. Okay, so write it as Ca, the symbol Ca for calcium, and you put that 2 plus charge in the top right corner. Okay, let's try another one here. Here we have phosphide. Okay, again, I pointed out that "ide" ending kind of tells you that we're dealing with a non-metal here. So immediately this makes your job a little bit easier because it narrows down where in the periodic table you're looking. It's somewhere in that top right section of your periodic table where all the non-metals hang out. Okay, so ask yourself, what non-metal starts with phosp? So the only candidate here is phosphorus, right? So if we look at phosphorus, it has the symbol P, and you look at that in your periodic table, and you see that's in group 15. Okay, so you've got to ask yourself, well, how many valence electrons does phosphorus have, and how many electrons does it gain to become like the non-metals? To become like the noble gases, sorry. And so phosphorus is in group 15, as I mentioned earlier, and so it has 5 valence electrons, and therefore it gains 3 electrons to reach the octet rule to become like the next noble gas. So in other words, the charge it's going to have is going to be a 3 minus charge. Okay, so we have letter P for phosphorus, and we put a 3 minus charge in the top right corner. Okay. A little note here about titanium being a transition metal. Most transition metals tend to have multiple charges. They have ions that different types of ions that have different charges. So you do need this extra piece of information in the name that tells you the charge of that ion. So here, by seeing the Roman numeral 4, what the question is telling you is that the charge is going to be plus 4. Okay, so in other words, we take the symbol titanium for titanium, which is Ti, and the periodic table won't tell us what the charge of titanium is because it's a transition metal. So you have to go off of that Roman numeral given to you. Okay. So the Roman numeral 4 tells you that it's got a 4 plus charge. There are a few exceptions to this rule. There are some transition metals and p-block metals that that do have fixed charges. Gallium's actually one of them. You may not have to really memorize gallium. I feel that's not a very common one. I think more common ones are like zinc or aluminium or silver. So aluminium tends to have a plus 3 charge. Zinc tends to have a plus 2 charge, and silver is plus 1. So that you don't really need Roman numerals for those elements. You kind of have to memorize what their charges are. Okay. All right, let's try doing this backwards. Here we have some symbols for elements using 1 or 2 letters, and we've got the charges in the top right corner that tell you what the charges are. Okay. Now notice that the charges here are written with the sign first and then the number. I was always, taught that, typically you want to write the number first and then put the plus or minus at the end when you're talking about charges. I tend to write out oxidation numbers in this format. The difference between a charge and an oxidation number is very subtle. So to be honest with you, here in Chem 103, it's not really an important distinction. All right, so if you write your charge first and then the number, that's totally acceptable. For this class. Okay, if you go to higher levels of chemistry, you may get some professors who are a little bit, a little bit more persnickety about it. But over here, it probably doesn't matter. Okay, so anyway, here we have carbon, right, with a -4 charge. Oh, sorry, I should point out that it's technically just letter C. You need to look up and figure out what is element C, and so that's carbon. Right? So we're going to take that name, carbon, okay, and ask ourselves, well, does that name change or does it stay the same? First of all, ask yourself, is carbon a metal or a non-metal? The fact that it has a negative charge should probably give this away, but it's a non-metal, okay, which means you're going to have to add that "ide" ending to the end. So we take the first syllable of carbon, which is carb, and we're going to add that "ide" to the end. So it becomes carbide is the name. Okay? All right, so it's carbide or carbide ion. Okay. Over here we have Rb, okay, with a +1 charge. Again, that positive charge should kind of give this away, or you could just look up the symbol Rb in your periodic table, and you see that it is a metal named rubidium. Now, because it's a metal, you don't have to change the name. The name just stays rubidium. And yeah, it's just rubidium. I guess you could add the word ion here. That's kind of what they've done in this section. But the key thing is the name does not change. It just stays rubidium. All right. Now, like as with our titanium example here, if you do have a metal that's not a group 1 or group 2 metal, you do need to put a Roman numeral to show what charge it is. Okay, so for example, here we have Pb. All right. Now, if you look up Pb, you'll see that that stands for lead. Okay. I know that sounds weird, that the name lead has a symbol Pb, but it comes from the Latin name plumbum, right? So the Romans used lead for plumbing, I guess. I guess we do too. Anyway, the lead being a p-block metal should have a Roman numeral showing what charge it is, because there's multiple kinds of lead ions out there. Here we have lead with a +4 charge, but it's possible to have lead with a +2 charge, for example. All right. So to show that we're specifically talking about lead with a +4 charge, we need to put the Roman numeral 4 over here. Okay. So for those of you who aren't as familiar with Roman numerals, either start paying attention to the Super Bowl, or just look up how to do this. But basically, you're never going to have to go to more than 8. That kind of limits the number of Roman numerals you need to learn how to use. So really the only symbols you're ever typically using are I's or V's. Okay, so just remember that a V represents 5. So IV is 1 before 5, and that's why it's a number 4. Now that we've practiced writing out the symbols and charges for actual ions, we want to combine this information to write out the names and formulas for compounds. Okay, so whenever you're given the name of a compound, it's always got 2 words. Okay, ionic compounds have a positive ion, which is listed first, and a negative ion, which is listed second. So when you're looking at problems like these, you need to write out the symbols and charges of these ions, kind of similar to what you did in this section up here. Okay, so let's start off with our let's see, magnesium nitride. Okay, so if we look at the symbol magnesium, the symbol for magnesium is Mg. Okay. The fact that there's no Roman numeral in here should tell you that magnesium's probably in groups 1 or 2, which makes looking up its charge relatively easy, right? So magnesium's in group 2, which means its charge is going to be 2+. It's going to have a +2 charge, because that's what all group 2 metals do. They have +2 charges, just like calcium in our example up here. Nitride, that's going to be our anion, our negative ion. That "ide" ending, of course, shows that there's this is a monoatomic ion. There's just one element making up this negative ion, and it starts with niter. Ask yourself, what nonmetal starts with niter? Okay. Again, your options are a little limited here, right? Your nonmetals are in the top right section of your periodic table, so hopefully this will be relatively easy to look up. But that's basically going to be nitrogen. Okay, nitrogen is the nonmetal that starts with niter. So the symbol for nitrogen is a capital N, and because it's in group 15, it's going to have a -3 charge because it gains 3 electrons to become like the noble gases in group 18. Okay, so we give it a -3 charge. Okay, that's the first step. We've got the symbols and charges for the ions making up magnesium nitride. Now we need to combine them to write out the chemical formula. Okay, so of course we want these positive and negative charges to balance. We need them to cancel each other out. Now, just glancing this, that's not going to happen, right? Because 2 and 3 are different numbers, right? They're not balanced. So we're going to have to alter the number of our ions in order to get this to work out. Okay, and we're going to show this with subscripts in our final formula. Now, there are a couple of ways to do this. You could simply just cross the 2 numbers. You can put the 3 down here next to magnesium, and you can take this 2 and put it next to the nitride. Don't move the charges, of course, because it's just an absolute number of ions. It's always a positive number. Um, so basically, the formula should be Mg3N2. Okay. So that's probably the simplest way to do this. Though I will point out that you want to make sure that this ratio is simplified. Sometimes if you use that crossing method, you don't get the simplest ratio, and you need to do that yourself before um, before you're done with the problem, right? Because like let's say this was a 4 and a 2. Well, both of those are divisible by 2, so they'd become a 2 and a 1 respectively. Okay. Now, if you want to avoid that issue, the other way to balance these numbers, these charges, is to ask yourself, well, what's the lowest common multiple of 2 and 3? What number can both of those numbers divide into and leave no remainder? The answer to that question is 6, right? 2 goes into 6 3 times, and that's why we have a 3 here. 3 goes into 6 2 times, and that's why we have a 2 here. Okay, so that's the lowest common multiple method of writing out a formula. Okay. Now, this problem, this section, has a few polyatomic ions in them. So notice that if your nonmetal has that "ide" ending, all right, it's usually it tells you that your non-metal, your negative ion is made up of just one element. It's a monoatomic ion. But you then have, and writing that out, it's obviously relatively straightforward. If it doesn't have an "ide" ending, if it ends with either "ite" or "ate," that tells you you're dealing with what's called a polyatomic ion, an ion made up of more than one nonmetal. Okay. Basically, you've got a bunch of nonmetal atoms that are covalently bonded together, but that molecule has a charge and therefore is able to do ionic bonding. Okay, this involves some either memorization or looking up the formula of these ions. So, for example, if we were to do actually either aluminum sulfide or, tell you what, let's try the copper 2 bicarbonate, because that gives us a good example of something with a Roman numeral. Okay. You need to look up what bicarbonate is, okay, or at least memorize it. Bicarbonate, if you look it up in a table of polyatomic ions, has the formula HCO3 with a -1 charge. Okay. Please note that's 1 hydrogen, 1 carbon, and 3 oxygens, and that whole thing has a -1 charge. Okay. I'd say that what throws off students here is when they see that 3 down there, they think there's 3 hydrogens and 3 carbons and 3 oxygens. No, it's just 1 hydrogen and 1 carbon. And so sometimes it helps if you kind of put the whole thing in parentheses just to consider, like, okay, this thing has a -1 charge. But that's something that you need to get used to here. Okay, it's a little different from monoatomic ions typically, because again, it's a little weird when you've got more than one nonmetal involved here. Okay, copper, of course, you've got to look up the symbol for copper. The symbol here is Cu. Okay, and if you're wondering why it's not Co, because that's cobalt, the copper symbol is Cu because of the Latin cuprum. I guess that's the name of copper in Latin. And anyway, what's the charge of our copper ion? Well, copper, being a transition metal, can have more than one charge. There are copper ions that have a +1 charge. There are copper ions out there that have a +2 charge. Which one are we dealing with? Well, the Roman numeral tells us. We've got a Roman numeral 2, which tells us that this is a copper with a 2+ charge. Okay, now balancing this should be relatively straightforward. We've got 2 positives here and only 1 negative over here. Okay, when you have only 1 positive, 1 negative, I usually don't bother writing out the number 1. It's kind of understood. But anyway, we've got that -1 charge, so we need to double the number of negative charges to balance out those 2 positive charges. right? So when we do that, we would normally put a subscript of 2 next to the ion we're dealing with. Now, in the case of monatomic ions, that's really straightforward, right? We've got a 2 here, and it's kind of understood that it belongs to that nitrogen there. If you put a 2 next to HCO3, that gets a little confusing for 2 reasons. One, depending on how you write it, it might look like you're saying that there are 32 oxygens, right? If the 3 and the 2 are right next to each other, it looks like you're writing the number 32, which is just kind of silly. The other thing to watch out for is that you want this whole polyatomic ion to be doubled. Okay, you want to show that that 2 applies to this entire polyatomic ion, not just that last element in it. Okay, so to accomplish this, we're going to put parentheses around that formula, and we're going to put our subscript outside of those parentheses. So when I'm writing out this answer, I would write down my copper as Cu, and I'd open parentheses and write out the symbol for HCO3, close parentheses, and I'd put my 2 outside of that. Okay, so now I've got 2 of these negative charge things balancing out the 2 positive charges on my copper ion, and that's how the formula is written. Okay, please note, for whenever we write out our ionic compounds, even though ions have to have charges, in your final formula where these are balanced, we don't write those charges anymore. Okay, it's understood that we balance them in order to get this formula right. So now we've got the formulas of these ionic compounds here. You can tell that they're ionic compounds because they've got metals and nonmetals typically. I think an exception to this would be when you've got the polyatomic ion ammonium as your cation. It's a polyatomic ion made of nitrogen and hydrogen, which are nonmetals, but it has a positive charge, so it behaves like a metal. So sometimes that's a little bit harder to recognize. But I think as soon as if you memorize that NH4 is ammonium and you know that that's a polyatomic ion, anytime you see that, you know you're still dealing with an ionic compound. Okay, anyway, my point here is that with these ionic compounds, we're going to name the 2 halves of that compound. You always name your positive ion and you name your negative ion, and that's it. You're pretty much done. Okay, so all you're doing here is you're splitting each of these into the 2 halves that make them up. Okay, so for example, in this first one we have Sr. You've got to ask yourself, well, what's Sr? What element is that? Okay, and the second half of this here, we've got the symbol I. You ask yourself again, well, what is I? What element does that represent? Okay, that's the 2 halves we're splitting this up into. Okay, basically, with in the case of this second example here, now you've got more than 2 elements. You've got a barium, you've got Ba, you've got P, and you've got O. Right? There's 3 capital letters here, so there's 3 elements making this up. So you've got to ask yourself, okay, how do I split this in 2? Okay, well, as soon as you recognize that P and O are both nonmetals, you should recognize that, oh, I must be dealing with a polyatomic ion here. It's made up of more than 1 nonmetal. The fact that this is in parentheses also kind of gives that away, so that helps. When you see parentheses, you know that you're dealing with a polyatomic ion, though, as you can see, that's not always the case. Sometimes, if there's only one of a polyatomic ion, they don't bother putting the parentheses around it. It's kind of understood that there's a polyatomic ion there. Okay. In this case, the polyatomic ion is further complicated by the fact that it's got chromium, which is actually a transition metal, not a non-metal. So that's a less common polyatomic ion. So you're probably not going to see that too often on a quiz or exam. Okay. Anyway, you can look up polyatomic ions. Pretty. We have a table of them here in this lab. So for the purpose of this lab, at least, you should be able to look them up. Okay. Alrighty, so let's write out the 2 halves of each of these compounds. So if I look at Sr and I ask myself, well, what element has the symbol Sr, and that's strontium. Okay, and as a metal, we don't have to change the name, right? It just is strontium. Since it's in group 2, you don't need any Roman numerals. It's all group 2 metals automatically have a +2 charge, so we don't need to add anything here. It's just strontium. Very easy. For the second half of this, we have the symbol I. Okay, now that stands for iodine. Now, notice that this is the only non-metal listed there. I know there's a 2 there, but since there's no other non-metals, that 2 is part of how we balance out charges and stuff. It's not a polyatomic ion, so we're going to write out the name of this non-metal with its "ide" ending because it's made up of just one non-metal, in this case iodine. So we take that first syllable-ish, it's iode, and we add the "ide" ending to that, so it becomes iodide. Okay, and that's it. There's a 2 in that formula, but that's just because we need 2 of these negatively charged iodides to balance out the +2 charge on strontium. We don't need to reference that anywhere in the name. The name is just strontium iodide. Very straightforward naming. Okay, so that's the great thing about problems like this where your your metal is a group 1 or group 2 metal or something like aluminium, where you know what the charge is going to be. There's no messing with any numbers or balancing anything. You just say name of my cation, name of my anion, and I'm done. Okay, it's great. Let's try this next one here. All right, so here we have a polyatomic ion, but again, it's pretty straightforward because we have a group 2 metal that we're just going to name, and then the name of that polyatomic ion. Okay, tell you what, let's try, because I don't want to do all of these problems. I wanted to give you guys a chance to do these yourselves. Let's try this problem down here, okay, to get an idea of how we can combine a problem with a polyatomic ion and a transition metal that needs a Roman numeral. Okay, so again, we split this up into our 2 halves. We have Fe, which is iron. Let's write that down. Okay. And we have ClO. Now, ClO is a polyatomic ion, right? You've got 2 capital letters here. We've got Cl, which is chlorine, and O, which is oxygen. Both of these are non-metals. So that should give away that this is a polyatomic ion. Okay, even if you haven't memorized your polyatomic ions, you can then look up in a table of polyatomic ions, what's the name of this? Okay, and ClO is hypochlorite. Okay, which, by the way, this is the active ingredient in bleach, in case you're curious. So hypochlorite is the name of that polyatomic ion. So I'm going to write out that name. And that's just a name. You don't have to worry about any "ide" suffixes or anything like that. It's the name is hypochlorite. Let's go with that. Okay. Now, I've left a little bit of a gap here, and if you're wondering why I did that, it's because iron is not a group 1 or group 2 metal. It is a transition metal that needs a Roman numeral to tell us what is the charge on that iron ion. Okay? So, we need to figure that out and put that Roman numeral here. Okay, unlike our group 1 or group 2 metals where no Roman numeral is needed, you just say the name of the metal and you're done. Here we need to do a little bit of extra work to figure this out. Now, our periodic table doesn't help us here because charges of transition metal ions are all over the place. So you kind of have to work backwards. You have to know the charge of your anion, in this case hypochlorite, and then ask yourself, well, what must the charge on my metal be to get this to balance out and give us the formula we see here? Okay, so to do that, let's first look up the formula of hypochlorite. Now, if you look that up, you'll see that it has a -1 charge. Okay, we don't know what the positive charge on our iron is, so that's a question mark for now. But we know that the positives and negatives of both sides of this have to add up. They have to balance each other out. notice that we have 3 hypochlorites balancing out just 1 iron. There's no subscript here, so that tells you there's only 1 iron. Well, if you've got 3 hyperchlorites and each of them's a -1 charge, well, that means that we have 3 negatives on this half of our formula, which means on this half we must have 3 positives, right? So, whoops, let's move that over here. It's kind of hard to write on here with all these crammed together. Okay, there we go. So +3 and -3. Well, what's the charge on each of our irons if one iron ion has a +3 charge? Well, it means each one must have a +3 charge. And so that's our mystery charge. This must have a +3 charge on that iron ion, and that's why we need 3 of these -1 charged hypochlorites to balance that out. So when we write out the Roman numeral for iron, it has to be the charge on that iron ion. Okay, so we write out the Roman numeral, Roman numeral 3. There we go. Iron 3 hypochlorites the name. All right. So yeah, that's basically it. So you have to figure out the charge on your ion, on your metal ion first, and write that as a Roman numeral. If you wrote iron hypochlorite, that's a little too vague because there's multiple types of iron hypochlorite out there. There's a version of iron hypochlorite which is iron 2 hypochlorite, where this number over here would be a 2. Okay. A common mistake that students run into on problems like this is they see, a number in the formula and they automatically want to put that as the Roman numeral. Now, sometimes that works out. In this example, it happens to, like, there is a 3 in this formula and the Roman numeral happens to be 3. But this 3 does not come from the 3 over here. Okay, this 3 comes from the +3 charge on our ion, on our iron ion, which is not shown in that formula. Okay, you have to do the math and figure that out. Okay, like I said, it's a coincidence that it works out here because hypochlorite happens to have a -1 charge. The numbers just kind of work out that way relatively simply. But that's not always the case, right? So if you had something that had a -2 charge, like oxide, for example, these numbers would not agree in that way, and you often get the wrong answer if you make that assumption. So please avoid that common pitfall. Okay, actually work out what must the positive charge on my metal be, and use that as your Roman numeral. Have covalent compounds. This section, I think, often comes up with a lot of relief to students, especially when they deal with all the rules in the previous section. Not that the rules themselves are difficult. I think it's just trying to get the hang of the rules that I think sometimes is, has a little bit of a learning curve to it, and I think sometimes students find that a little bit frustrating until it clicks. But with covalent compounds, I think most, most students universally like covalent compounds because all you've got to do is memorize your Greek prefixes, and there's no math involved. It's you have a very simple format for naming covalent compounds. Okay, so like with ionic compounds, you have you have sort of 2 parts to each of these names. All of these covalent compounds are what we call binary covalent compounds. They're made up of 2 elements. Okay, and just like with our ionic compounds, we're going to name the first element with just its name. All right, we're not going to change it. And with the second element, we're going to add an "ide" ending to it. So you'll notice that all of these examples here end with "ide," like oxide, chloride, fluoride, etc. Okay? But you'll notice at the start of these words, we have certain Greek prefixes like di or mono or tetra, penta, tri. These are all Greek prefixes that reference some sort of number. Okay? Now, you do need to memorize these prefixes. However, I recommend thinking about the English or thinking about English words that have these Greek roots because that makes it a little bit easier to remember the meaning of those words. So for example, mono means one. Okay, so for example, a monocle is just one eyeglass that goes over a single eye, like kind of like what Mr. Peanut wears, right? Or a monopoly where one person owns everything, right? Die means two. Tri is three. Think of like a triangle or a tricycle. Tetra means four. Think of the video game Tetris. Where if you're, a Tetris is where you clear four lines at once. Now, Tetris is a Russian word, but it comes from tetra, which is the Greek root of that word. Okay, and so on. Once you start getting to penta, now you're getting to geometry terms, right? Like a pentagram is a five-pointed star, or a pentagon is a five-sided polygon. So penta means five, and so on. Okay, so whenever we see names like this, recognizing those Greek prefixes tells you, oh, you've got dichlorine. Well, that means there are two chlorines. So I look up my symbol for chlorine. Okay, that's Cl. And the di over there tells me that it's got a subscript of 2. Likewise, if I see monoxide, the mono tells me I've only got one of that element. And oxide, well, if I drop that ide, I've got ox. What nonmetal starts with ox? Again, you're dealing with the nonmetals, which are in the top right of your periodic table, so your options are kind of limited here. So hopefully you quickly realize that ox is the start of oxygen, which has the symbol O, and of course the mono there tells you there's only one of it. So we don't bother writing a subscript for one of something. It's understood that there's one of it. Okay, so there's your formula. Okay. Now a quick note here about the mono prefix. If your second element has to have a prefix, so if there's only one oxygen, you have to say that it's mono. Your first element occasionally will not have a prefix to it. That just means that there's one of that element. So for example, carbon tetrafluoride has one carbon and 4 fluorines. You don't need to say monocarbon tetrafluoride. It's kind of understood when you just say carbon that there's one of it. But you do have to write mono if there's only one of a second element. Okay, that's the only situation where you'll ever see mono written. Okay, but yeah, otherwise, be on the lookout for prefixes at the start of each of these words. Okay, and if you don't see a prefix, if you just see a chemical symbol, though, to be honest with you, I think memorizing the prefixes is a little bit easier, and you can see that there's no Greek prefix, mono, di, tri, tetra, penta, hexa, etc. None of that's written in the front of this name here, so I know there's only one carbon. Okay. Over here we've got formulas, and we're going to try and go backwards. Okay, so again, these are all non-metals or metalloids in some cases, so we know we're going to use our covalent rules here for naming these. All right, so if I look up As, I ask myself, well, what element is that? And that turns out to be arsenic. Okay, since there's only one of it, as evidenced by the fact that there's no subscript, I don't need to add a prefix here. Okay, and including I don't need to write mono. It's understood if I write arsenic, it's just one arsenic. Now here I have I, which stands for iodine. Okay, but again, since it's our second element listed, we need to write out, with that first syllable, iod, and add that ide ending to it, so it becomes iodide. Now, of course, though, you do need a prefix, and here there's 3 of those iodides, so it becomes arsenic triiodide. Now, when you have redundant, you have 2 vowels next to each other, I've seen this written both ways. So triiodide, I think, is probably a correct way of writing this. Sometimes you can drop that I and just call it triiodide. I don't think I hear that as often. I think most people say triiodide, and that's okay. But you can see here in the case of monoxide, we drop that second O. We don't say monooxide, it's monoxide, right? So something to watch out when you have 2 vowels next to each other when you combine a prefix and the name of an element. Okay, so if your element starts with a vowel, that's something to be aware of sometimes. In this section here, we're going to name acids. All right, we'll spend an entire chapter talking about acids and bases and their names, but and their properties really is where what we'll spend most of the chapter talking about. But that chapter is all the way at the end of this course. It's chapter 12, and you're going to be using acids and bases and stuff in lab well before that last chapter. So it might be useful to get the hang of naming some common acids and bases. In the case of acids, naming them is pretty straightforward. They typically end with the name acid, so at least that makes it a little easier to recognize if you see the name written out. We have two types of acids that we deal with. We have, basically you have hydrohalic acids, so they start off with hydro and then something ic acid. All right, and what that means is that you have a hydrogen, right? And you can look at the root word of that's in the middle of the name here and ask yourself, well, what halogen is that? What group 17 element is that? The iode here comes from iodine, so we know that this is balanced out with an I for iodine. Okay, now the balancing this out is very straightforward because a hydrogen ion has a +1 charge because hydrogen's in group 1, and an iodide, being a halogen, has a -1 charge because it's in group 17, so it gains 1 electron to become like the noble gases. So balancing this out is really easy because +1 and -1 cancel each other out. Okay, so naming your hydrohalic acids or writing out their formulas is really, really straightforward. Okay. Now, in the case of other acids, okay, you want to pay attention to if it has an ic or us ending. Okay, for each of these types of acids, you have a polyatomic ion that just has hydrogen ions balancing out its charge. Okay, so if you see an ic ending, you want to think of a polyatomic ion that has an ate ending. So for example, carbonic acid comes from carbonate. Okay, so you've got to ask yourself, well, what's the formula and charge of carbonate? Well, carbonate is CO3 with a 2- charge, right? And so you need to balance out those 2- charges with hydrogen ions, and so you need 2 hydrogen ions to balance that out. So the formula of carbonic acid winds up being H2CO3. The number of hydrogens you need has to equal the negative charge on your polyatomic ion. Okay, so that's basically how you do that. You have to look at your ending and ask yourself, well, what's the polyatomic ion that starts with, carbon and ends with 8, and in this case carbonate. Now if you see an us ending, that means you want to look for a polyatomic ion that ends with ite. Okay, so an ic ending means you're looking for 8. Us means you're looking for ite. So in this case, you want to look up chlorite. Chlorite has the formula ClO2 with a -1 charge, as opposed to chlorate, which is ClO3 with a -1 charge. So chlorite is ClO2, and so if we want chlorous acid, we just have to add H pluses until that's balanced out, which in this case, since it's got a -1 charge, this is pretty straightforward. The formula is just, HClO2. There we go. Okay. Now, you can see here that we have, basically kind of a similar thing here. All of these are polyatomic ions. Here we have HCN. This one's going to be a little bit interesting. Out of all the polyatomic ions we've seen so far, cyanide and hydroxide are 2 polyatomic ions that don't end with ate or ite. Rather confusingly, they end with ide, which kind of implies a monoatomic ion, which obviously they're not. Cyanide's made up of carbon and nitrogen, and hydroxide is made up of hydrogen and oxygen. Okay, so you do have to kind of memorize that. So naming this would be with that "ide" ending. You can't use the "ik" or "us" system as easily. So this is actually another one of those acids that starts with hydro. Okay, this is hydrocyanic acid. All right, which might be something you just have to memorize. So let's try another example here, based on based on the names of the polyatomic ions making them up. Okay, so if I look at the second example here, okay, we have H2C2O4. The fact that I've got two hydrogens starting this off tells me that the polyatomic ion C2O4 must have a 2- charge balancing that out. Okay, so I ask myself, what polyatomic ion is C2O4? Whoops, C2O4 with a 2- charge. Okay, what is the name of that? And it turns out that that's oxalate. Okay, so I take that name oxalate and I drop the 8 and I add "ic" at the end. So it becomes oxalic acid. Okay, and that's how you approach that. Okay, so that's an example of something that has an 8 ending, and so it becomes an "ic" acid. Here we have HNO2. Now, NO2 with a -1 charge is nitrite. So this becomes nitrous acid. Okay? So NO2 minus is nitrite with an ITE ending, and so the acid must have us, OUS, in the name. All right, now this next section involves hydrates. To be honest with you, this isn't a super important topic for Chem 103. We don't deal with hydrates a lot in this class, so you're probably not going to see this show up on the final or anything like that. In any case, though, if your instructor wants you to do this section, you can. Really, that applies to this whole lab report. This is a very long lab report, so I really doubt your instructor is going to ask you to do every single thing, because that's probably a lot of grading for them. It might be a good practice for you. It might not be a bad idea to do this whole lab report for your benefit, just to get ready for an exam or get more practice in. But I'm guessing they're probably going to say, like, hey, make sure you do only these select problems, at least these select problems. So talk to your instructor about which sections you need to do and how many questions from each section you need to do. But that being said, hydrates is one of those things that I think most of us instructors would probably drop from this lab because it's not as important a topic. But that being said, if you do ever come across them, essentially all of them follow this format where it's the formula of some ionic compound and you name it as such. There's a dot followed by a certain number of water molecules. Okay, now this represents how many water molecules are embedded in the crystal structure of this of this ionic compound, and you're looking at the ratio of water to the ions making up your ionic compound. So what we do is we just take that number and we use a Greek prefix to represent it. So in this case, heptahydrate means that there's 7 waters. Okay, so we add heptahydrate as a suffix to the end of this to say how many waters there are. So if you're given a name for any of these, you take the first 2 words and you write out the formula. So magnesium sulfate, well, we need the symbol and charges of those. Magnesium is Mg, which in group 2 means it'll have a 2+ charge. Sulfate is a polyatomic ion. You can tell from the 8 endings. You've got to look that up if you haven't memorized it. And it's SO4 with a 2- charge. So when we balance this out, well, 2+ and 2- balance out pretty easily. So it's just MgSO4. Please note the 4 here doesn't mean there are 4 sulfates. SO4 is one thing. Okay, so yeah, so you got to get used to that, of recognizing those polyatomic ions with more than one nonmetal. Anyway, the hepta part, like I mentioned, means that there are 7 waters. So we put a dot here and we put 7 H2O. oops, go, dot 7H2O, and that's the formula of magnesium sulfate heptahydrate. Okay, so likewise here, if you're given a formula, you've got to name the ionic compound at the start of it. So CO is cobalt. Since cobalt is a transition metal, it's not group 1 or group 2, we're going to need a Roman numeral for it, so I'll add that in a second. SO4, of course, is sulfate. Okay, so depending on if you're American, you might spell this with a F instead of a PH. Okay, I sometimes go back and forth. Anyway, so sulfate has a 2- charge. So what must the charge on that cobalt be to balance that out? Since there's only one of each ion, that cobalt must have a +2 charge. Okay, so it's cobalt 2 sulfate. And since there's only one water here, that would be monohydrate. Okay, so I'm running out of room here, but it should have the word hydrate. I'm just going to abbreviate that there. Okay, so that's cobalt 2 sulfate monohydrate. Okay, over here, for example, we have sodium chromate tetrahydrate, for example. Okay. Finally, we have this section here, and I dare say this is probably the most useful practical section for you in this lab report. One of the biggest issues with nomenclature and writing out formulas is that students, when you see this on a quiz or exam, it doesn't tell you what type of problem it is. You're expected to recognize it and write out the name or say the name or write out the formula or whatever. And the problem is trying to keep the rules straight in your head. Your first step, and it's kind of unwritten here, is to first classify what type of compound are you dealing with so you know which rules to apply. All right. So basically, this section here, part 5, you can see we've got a lot of problems in here, both like formulas and names. Looks like we got about 20 formulas and another 20 names, right, to give us 40 problems. This is a just mixed bag of different types of problems that we've already seen, and it gets you to practice writing out, the appropriate name or formula, and it doesn't tell you what type of problem you're dealing with. That's this first section here, where you've got to say, okay, what am I classifying this as? Okay, what type? Is this an ionic compound? Is it a covalent compound? What rules do I follow? And then, if you're given a formula, you write out the name here, okay, based on the rules that you would use for that type of compound. Okay, or for questions 21 onwards, since they give you names, you then have to write out the formula over here. Okay, so my advice is to first look at this and ask yourself, okay, do I have any metals in this? So you look up this first example here, we have C and we have O. Well, C stands for carbon and O stands for oxygen. Both of those are non-metal. So immediately, I know that this is going to be a covalent compound. Oops, I guess you can, I don't know if you want to write out the full word covalent. I mean, I think you could probably abbreviate this if you want and just write, cove or something like that. But yeah, so basically, as soon as you recognize this is a covalent compound, now you can use covalent rules for naming this, where you have to write a Greek prefix to represent the number, right? So this becomes tri, and C, of course, is carbon, so it becomes tricarbon. And there's 2 oxygens, so it becomes di for 2, and we take that that first syllable ox and we add I to it, so it becomes tricarbon dioxide, and that's the name of my compound. Okay. Likewise, now here for Rb2CO3, I have to ask myself, well, Rb, that's a metal, so I know this is immediately going to be an ionic compound, right? Because we've got metals and non-metals here. Once you realize it's an ionic compound, you may have to do a little bit more thinking or a little bit more classifying on how we use this. So as soon as you recognize, like, okay, carbon and oxygen are both non-metals, so I have a polyatomic ion here, something that's made up of 2 different non-metals. So I need to look up the name of CO3. Okay, now CO3 happens to be carbonate, and you also have to ask yourself, well, does rubidium need a Roman numeral? What group is Rb in? Well, it's in group 1, so like all the group 1 metals that all automatically have a +1 charge, you do not need a Roman numeral for this. So the name is very straightforward. It's just rubidium carbonate. Okay, and that's it. That's the name. You don't need any Roman numerals, don't need to do any math. It's understood. Okay. Now sprinkled in here we have a few acids. So for example here you can see if it starts with a hydrogen, chances are it's an acid of some sort. They've helpfully written an AQ after each of them to show that, okay, these are dissolved in water, and for something to act as an acid it needs to be dissolved in water, so that kind of gives it away. Okay, so for example, you have to look up the name of this polyatomic ion, and then accordingly, well, first of all, recognize this as an acid and name this accordingly. Okay, so you say, all right, what's CrO4? Well, that's chromate, so this becomes chromic acid. Okay. Again, if you notice that you've got only one non-metal attached to your hydrogen, then it becomes a, hydro acid of some sort. So this becomes like, hydrophosphoric acid, for example. All right, and of course down here where we've got the names, same process as before. You identify what type of compound you're dealing with. In the case of the ones that end with acid, that's really straightforward because you automatically know it's an acid. And of course, then going off that ic or us ending, or if it starts with hydro, you can name those accordingly. All right. So for example, here we have perchloric acid. Okay. So of course, first of all, it's an acid, so make a note of that. Okay. And so with that ic ending, that means we need to look up the formula of perchlorate, right? So if you see that ic ending, your polyatomic ion ends with ate, A-T-E. Okay, so perchlorate has the formula ClO4 with a -1 charge. So that tells you you're going to need only one hydrogen to balance out that -1 charge. And then of course you just need the perchlorate formula. Oops. So HClO4 is your perchloric acid. Okay. For all the others, of course, you need to know. First ask yourself, okay, am I dealing with a metal? Do I start off with a metal, or if you recognize a polyatomic ion, that kind of tells you, all right, I'm dealing with something that's ionic. Okay, so I just need to balance out the charges for the things making this up. So I draw the formula for potassium, which is K for potassium, which is in group 1, so it has a +1 charge. Permanganate. This one you're going to have to look up. That's a less common polyatomic ion. But for those of you who looked it up, it's MnO4 with a -1 charge. So when you balance this out, +1 and -1 cancel each other out. So the formula is just KMnO4. Right. And then, of course, if you notice that you're dealing with, your first word is a non-metal, then that makes, naming this relatively straightforward. So, for example, here we go, tetraiodine non-oxide. So again, you're starting off, anytime you see Greek prefixes, like you can see here diphosphorus tetrafluoride, seeing those Greek prefixes immediately tells you, all right, I'm dealing with something covalent. And so tetraiodine, okay, I've got 4 iodines, right? Because tetra means 4. And of course, the symbol for iodine is I. Nona-oxide. So again, nona here is the prefix for 9. And ox, it tells you you're dealing with oxygen. So I've got 9 oxygens. So I4O9. Okay. Again, notice we have 2 vowels here. So again, this is one of those situations, kind of like triiodide, where even though it seems like you ought to drop that first syllable and just call this non-oxide, sometimes in practice that's not the case, and people just know it as non-oxide. But anyway, yeah. So that's basically it for this section. So again, you've got these questions and problems afterwards. So talk to your instructor to see whether you need to do these questions or not. They might, given the number of problems that we've got working out here, they might just have you only do that. In this section, we're going to draw out Lewis structures. Now, Lewis structures are basically pictures of molecules that show where the valence electrons are in those molecules. So we represent electrons as dots around our atoms. And to show that electrons are shared between two atoms forming a covalent bond, we oftentimes will draw those as a line between the two atoms that are sharing those electrons. Okay, so anytime you see a line between two atoms, just realize that a single line has two electrons in it. Okay, another thing to watch out for here is that we're going to deal only with even numbers of electrons. All right, it's possible to have unpaired electrons. Those are what we call radicals. But to be honest with you, you are not going to see those in this course. That's a little bit more of an advanced topic that you'll see if you keep on studying chemistry, but we don't cover that in Chem 103. All right, so if you have an odd number of valence electrons, you've probably made a mistake somewhere in counting. Okay, so that should be a red flag that you should double check your math when adding up your total number of electrons, or total number of valence electrons rather. Okay, all right, so let's talk about how to draw these Lewis structures. Now, once we draw them, we'll have a few follow-up questions. We're going to ask ourselves, what shape do these molecules take? Are these molecules polar or not? Those are kind of the key questions we want to answer here. There's some other questions in this lab report, and you can talk to your advisor, to your instructor about whether or not you should answer all the questions, whether they're all completely necessary. Again, like the previous section with nomenclature, I'm sure your instructor probably has only so much they're willing to grade here. So talk to your instructor and see if you do need to draw everything. If you're one of my students, I'll say that the important things I want you to represent over here are the total number of valence electrons. Obviously, you're going to need that as part of your your calculations to draw this Lewis structure. You want to draw your Lewis structure. Now, there's a line in here that mentions that if there are multiple resonance structures, draw all of them. You might have only so much room here to draw, so I would say that if you can't fit all the resonance structures in here, just maybe draw one resonance structure and mention how many resonance structures there are. Okay, if you can figure out how many resonance structures there ought to be, that's fine. I think that's sufficient to show that you know how to do it, as far as I'm concerned. The polarity of the molecule is pretty important, and the molecular shape. So these two questions here are questions I want you to answer. Are there any polar bonds in this molecule is also a good one to answer. Though usually the answer is oftentimes yes, just because different elements have different electronegativities. So chances are the bonds are going to have some polarity to them. In terms of things that you can skip and get away with, this section over here that says to draw a 3D model sketch, for most, or at least a lot of the molecules, this is going to be kind of unnecessary. 3 dimensions really only come into play when you're dealing with 4 electron groups coming off your central atom. So, for example, if you have a tetrahedral molecule or trigonopyramidal, here, actually, let me scroll up here so you can show you what I'm talking about. So here are some sketches of different shapes. You can see that for a linear molecule or a trigonal planar or bent with one lone pair, these are all in the plane of the paper. They're two-dimensional. You don't really need to draw a 3D molecule here, so it's kind of silly. So really, it's only with tetrahedral molecules and things that are in that vein, so like trigonal pyramidal, where you've kind of swapped out one of those atoms for a lone pair, or the kind of bent molecule where you've got two lone pairs. These are the only ones where you're dealing with a bond angle of 109.5 degrees, and you can't, this molecule isn't flat. It exists in 3 dimensions. That being said, if you're one of my students, I'm okay with you not drawing the 3D sketch. To me, the very useful thing to get out of here is drawing a Lewis structure correctly, figuring out its shape, and figuring out is it polar or not. What intermolecular forces will it have? Those are kind of the key questions I want you thinking about when it comes to this section. All right, so let's get over here. So let's try a few of these different problems out, and we'll go from there. All right, first up, let's try out, this first example. I think this is a good example of, what to do when you have, things that have hydrogen in them, for things that have lone pairs in the central atom, stuff like that. Which I guess I'm kind of getting ahead of myself here. Let me draw this out, and you'll understand why I'm looking at those things. So let's start off by figuring out the total number of valence electrons we're dealing with here. Okay, so when you look at a formula for something, you want to look at the group that each of those elements are in, and that should tell you how many valence electrons that atom has. Now, please note, you want to use the number of valence electrons. Please do not use the total number of electrons or the atomic number of these elements. It's only those valence electrons, those outermost electrons, that the atoms use for bonding. Their core electrons are kind of hidden, and they can't really access any nearby atoms, right? They just can't reach. So we can't really count those when we're trying to figure out how the bonding works. Okay, so we have over here hydrogen. Hydrogen's in group 1, so a hydrogen atom has 1 valence electron. Okay, so now there are 2 hydrogen atoms here, so basically we want to take into account that we've got 2 of those, and each of them has 1 valence electron, so take 1 and multiply it by 2. And then we have sulfur. Sulfur is in group 16, or group 6A if you have an older periodic table. As a result, that should tell you it has 6 valence electrons. Okay, so we have 6 electrons for the sulfur. So when we add this up, our molecule should have 8 valence electrons. Okay, so I guess I should write that there. All right, you have 8 valence electrons. So I'm kind of showing my math here, but this is basically where I figured out that the whole molecule has 8 valence electrons that should be represented. Okay, so when we're drawing a good Lewis structure, the 2 key things that I want you to show here are, do we have the right number of valence electrons, and is everything meeting the octet rule? Okay, now when I say everything, there's a caveat there. Hydrogen does not meet the octet rule. Okay, hydrogen, the nearest noble gas to hydrogen is helium, which has only 2 valence electrons when that 1s orbital is filled. So hydrogen actually obeys what's called a duet rule. Instead of trying to have 8 electrons, it only wants 2 around it, which it pretty much gets by forming any bond, any single covalent bond. So never draw lone pairs on hydrogen. Okay, unlike any other atom where you can put lone pairs to show that the atom's meeting the octet rule, in the case of hydrogen, do not do that. Okay, so so those are the 2 key things. You want to make sure that everything's meeting the octet rule if it should, and we have the right number of valence electrons shown in the diagram. Okay, if you get the wrong number, that's usually a hint that there needs to be a double bond or something in there. Which, by the way, I recommend using a pencil when you're drawing all of this stuff out, because you might find you've got to erase stuff, especially when you realize that you need double bonds or triple bonds or things like that. All right, so Now, when we're starting off here, you want to pick your central atom. Now, typically, your central atom is the first element listed. However, if your first element listed is hydrogen, that can never be your central atom. As I mentioned, hydrogen only forms one bond because that's the room it has for the number of electrons it can use. So it's very lousy as a central atom because only one thing can sort of stick to it. All right, so if your first element's hydrogen, then that's not your central atom. So go to the next thing, which is in this case sulfur. So sulfur is going to go in the middle here. Okay, there are two hydrogens, so draw each of them connected to your sulfur. Okay, now how you do this is up to you. I like to draw atoms, sort of, like this. I'm eventually going to figure out that this molecule is bent, and I'll show you how I figured that out. But I'd like to draw bent molecules like this to remind myself that they're bent, because this is one of the dangers of trying to draw a three-dimensional molecule on a two-dimensional sheet of paper. But that being said, if you want to draw both hydrogens on a straight line, by all means, feel free to do that, okay? As long as you're meeting the right number of electrons and things are meeting the octet rule, how you draw it is fine. You just have to recognize when you're writing out the shape that the molecule isn't linear, okay? That in 3 dimensions, that molecule's bent, okay? Anyway, we'll come back to that concept, that thought, once we finish drawing this molecule. Okay, so I've got all my atoms here. Okay, I've got my sulfur in the middle, and there are 2 hydrogens connected to it. Remember, the 2 things I'm trying to meet here are I want everything to meet the octet rule, and I want to make sure I have the right number of electrons. Start off with the octet rule. I find that it's easier to get that out of the way. I find that students who start worrying about number of electrons first tend to make a mistake with the octet rule later on. They kind of forget to meet the octet rule. As soon as they see they have the right number of electrons, they stop right there, and oftentimes you wind up having an incorrect Lewis structure because something's not meeting the octet rule. So my advice is start off with the octet rule because that's an easy one to get out of the way, and it's easier to avoid mistakes. So with the hydrogens, of course, they don't need to meet the octet rule. They're fine with the 2 electrons they have, that they're sharing with the sulfur in that bond, and this hydrogen's happy with that bond. But let's look at the sulfur, okay? Now, if I count the number of electrons around my sulfur, I've got 2 electrons in this bond and 2 electrons in this bond. Well, that's 4 electrons. And remember, if sulfur is part of a molecule here, as I'm trying to draw it, it should have 8 electrons around it. Okay, so we need to draw those extra electrons, and we do that by giving that sulfur lone pairs. Okay, so we give that a pair of dots over here and a pair of dots over here. Okay, so now if I'm counting each of my pairs of electrons here, 2, 4, 6, 8, my sulfur is meeting the octet rule and it is happy. Okay, and that's a good thing. Things to watch out for here when it comes to counting numbers of electrons and common mistakes students make here. I think the biggest question I get is, why does sulfur have to have 8 electrons? I thought we said it has 6. A sulfur atom that's not bonding with anything, that's just by itself, that has 6 electrons. Okay, 6 valence electrons, I should say. When sulfur is part of a molecule, or when any atom is part of a molecule, it's going to meet the octet rule. Okay, that's kind of what it's doing by, forming that molecule in the first place. It's trying to achieve some stability, and hopefully, if you've drawn your Lewis structure correctly, it would have already achieved that. So we're showing the sulfur as it should be, not as a sulfur atom is when it's by itself. Okay, so that's why we want to have 8 electrons around our sulfur, even though a sulfur atom has only 6 valence electrons. Okay, a quick way to make sure that you are counting correctly really quickly is if you imagine the sulfur as having kind of a box or a square around it, you should have two electrons or a pair of electrons on each side of the square. Okay, so if you imagine, a sort of just a little square around there, there's two electrons on this side, two electrons on this side, two electrons on this side, and two electrons on this side. Okay, please note that these single lines are two shared electrons. Which, by the way, I don't know if you noticed when I was counting these earlier, I tend to just count in even numbers that way. 2, 4, 6, 8. Since we're not dealing with radicals, I wouldn't worry about counting individual electrons. I find that, people tend to get confused that way. It's easier to count in pairs, I think, and not lose track. Okay, so so that's how we know that the sulfur is meeting the octet rule. So that's one thing taken care of. The next thing is the total number of electrons. Okay, so does this diagram show 8 valence electrons? Okay, so now I'm counting just the total number of electrons, and whether in lone pairs or in bonds, in this whole diagram. And it's going to be pretty straightforward because it's 2, 4, 6, 8. There aren't any lone pairs on the hydrogen, so really it's just these 8 electrons that are here that are the only valence electrons we're showing, and therefore this is a good Lewis structure. Okay, if this diagram had more than 8 electrons, that would tell me that I need to form a double bond or something. I'll do an example of that later on to show you. Okay, but yeah, so we're done here. Okay, in terms of drawing this Lewis structure. Okay, don't worry about resonance structures here. Resonance structures come into play when you have options of where to draw a double bond. So don't stress about that for now. Okay, I'll do that in another example. Okay, are any of the bonds in this molecule polar? So in other words, look at the covalent bonds we're dealing with and ask yourself, what's the difference in electronegativity between a hydrogen and a sulfur? Is there a difference in electronegativity? And the answer is yes. Those are two, different elements that have different electronegativities. So that bond is going to be a polar covalent bond. Okay, so I'm just going to go ahead and circle yes there. Now, if you want to draw a 3D model sketch, feel free to do so here. We've got 2 bonds and 2 lone pairs coming off of this central atom. So that's, you're going to see this shape here that this is a bent molecule. And this type of bent, as I pointed out earlier, looks kind of like this. There's a 109-degree bond angle, or 109.5 roughly. And again, that's a 3-dimensional molecule. This lone pair is sort of sticking into the paper. This lone pair is sticking out towards you. Okay, so you can draw this molecule basically in 3D here if you'd like. But that being said, if you're one of my students and you want to skip this section, that's fine. I'm mostly going to be grading you on the Lewis structure being correct and the molecular shape and polarity and stuff like that. Okay, but that being said, since we have 4 electron groups coming off of our central atom, right? So if I count the total number of atoms and lone pairs coming off of it, I've got 4 of them. So that's a 109, or roughly 109.5 degree bond angle. Okay. Now, what shape are we dealing with here? Okay. So the different shapes we deal with are linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. Okay, there are more complicated shapes than that, usually when your central atom exceeds the octet rule, as things in period 3 and below can do. There are certain exceptions to the octet rule, and those molecules will have more complex shapes. But as far as this class is concerned, we stop at tetrahedral. Okay, so how do we know the difference between those different shapes, or how do we recognize which shape we're dealing with? Well, I find that the easiest way to remember the different shapes is to kind of break this down into chunks. All right, ask yourself, how many atoms are connected to my central atom? So on your central atom, and then ask yourself, does that central atom have lone pairs? Oops. Okay, does it have lone pairs or not? Okay, so if there's one atom coming off your central atom, well, the molecule has to be linear because there's only two atoms involved and there's a straight line connecting them. But if you have two atoms connected to your central atom, okay, you have two options, right? It can either be a linear molecule or it can be bent. It's linear if there are no lone pairs on that central atom. It's bent if there's one or two lone pairs on that central atom. So in this case, this sulfur has two atoms connected to it, and the fact that it also has lone pairs tells me that this molecule is going to be bent. Okay. All right. So please note, I've drawn my bent molecule like this because I kind of knew heading into this problem it was going to be bent because I've seen a billion Lewis structures over the course of my life. You probably aren't at that point yet, and that's okay. So if you've drawn your Lewis structure to look something like this, okay, and you've drawn your lone pair up here and your lone pair up here, very symmetrical. That's okay. This is still a correct Lewis structure because we've drawn the right numbers of bonds and lone pairs. However, you have to recognize that this molecule, as you've drawn it, is still bent. Okay, you might be tempted to look at this and say, hey, the hydrogen, the sulfur, and the hydrogen are all in a straight line. That's linear, right? No, because what you don't realize is that these two lone pairs are pushing these two hydrogens closer to each other towards you. Okay, in the lecture video attached to this, to this chapter, I do use balloons to explain this. They make great space filling models that kind of show you, okay, why does this molecule take this shape in 3 dimensions? Okay, so if you're having trouble wrapping your head around what I just said, I really recommend watching that part of the lecture and thinking about, okay, what does this look like in 3-dimensional space? Okay, yeah. So the next question to ask yourself is, what implication does this have for our molecule? Is our molecule going to be polar or nonpolar? Now, what does that mean? The quickest way to figure out if a molecule is going to be polar or not is to look at your central atom and ask yourself, is everything coming off of that central atom the same? Okay. If you have different things coming off your central atom, it's going to be polar. Okay. Think of the opposite poles on a magnet. The north pole and the south pole on a magnet are different from each other, right? In the same way here, this sulfur has two hydrogens and two lone pairs. We have a hydrogen half to the molecule, and we have a lone pair half to the molecule. Okay, so that means that this is a polar molecule. Okay, if everything coming off of my central atom were the same, then that molecule is going to be nonpolar. Okay, that means it's very even. Okay, all that electron density is evenly distributed around that central atom. Okay, all right, so let's try another problem out that's going to be a little bit different. So let's try this very next one. Okay, COCl2. Okay, so let's add up the number of valence electrons that each of these atoms contribute. So carbon is in group 14, so it has 4 valence electrons. Oxygen is in group 16, so it has 6 valence electrons, just like sulfur does. They're in the same group. Now here we have 2 chlorines, okay, so whatever number of valence electrons each chlorine has, we're going to multiply by 2 because there's 2 chlorines. Chlorine's in group 17, so it has 7 valence electrons. So if we take 14 plus 6 plus 10, that's 24 electrons. Okay, so let's start drawing this. Our carbon is the first element listed, so let's draw our carbon in the middle there. And we're going to draw our oxygen and our 2 chlorines attached to that. So we'll start off by drawing them attached with single bonds. We have an oxygen, we have a chlorine. Let's draw another chlorine here. All right, there's our 3 atoms that are connected to our carbon. Let's now give everything the octet rule. Okay, so if I look at this chlorine over here, there's 2 electrons in that bond that's attached to it. So I need to give it 6 more to get to 8. So 2, 4, 6, 8. All right, that chlorine is now happy. It's meeting the octetual. Same thing for this chlorine over here. 2, 4, 6, 8. Probably want to do the same thing for this oxygen. I should have drawn this a little bit lower because there's a lone pair up here, but I'll try drawing that a little bit bigger so it's easier to see. 2, 4, oops, 6, 8. Again, if you kind of imagine a box around each of these atoms, there's a pair of electrons on each side of the box. So that leaves us with this carbon. Does the carbon meet the octetual? 2, 4, 6. Ooh, it needs 2 more. So let's put a lone pair over here. Now that carbon is meeting the octetual. Oops. Okay. All right. So here, everything's meeting the octetual, which is great. But let's make sure that we've got the right number of the total number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There are 26 electrons in this diagram. Uh-oh. So that means that if we have too many electrons, that means there needs to be a double bond in here somewhere. So again, we're going to fix that by erasing some electrons and drawing some bonds, which again, hopefully you've been drawing this in pencil. Okay, it's for this reason that we're going to do this in pencil now. So how do we draw a double bond? Well, pick 2 atoms that are bonded to each other, and so for example the carbon and the chlorine, or the carbon and the oxygen, or the carbon and the other chlorine for that matter. Remove a lone pair from each of them and then add another bond between those same 2 atoms. Okay, so let's say I pick this oxygen over here. Okay, I'm going to erase that lone pair that's on top here. Oops, that's not. Oh, there we go. That's how I erase that. Okay, so I've erased that lone pair there. I'm going to erase the lone pair from this carbon as well. Okay. And I'm going to draw another bond between those 2 atoms that I erased lone pairs from. Now, if you noticed, I removed 4 electrons, right? 2 from the oxygen, 2 from the carbon, and I only put 2 back in the form of that bond. Now, please note, by adding that bond between those 2 atoms, I'm still keeping the octetual for those 2 atoms. Notice that that oxygen has 2, 4, 6, 8 electrons around it. Likewise, that carbon has 4 bonds and therefore 8 electrons around it. Okay, 2, 4, 6, 8. But since I've taken away 4 electrons and only added 2 back, we've dropped 2 electrons overall. If you don't believe me, let's try counting these. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. This is now a good Lewis structure. Okay. Now, resonance structures are a phenomenon that come up when you've got to consider, could I have put that double bond in a different place? So I selected, I chose to draw this double bond between the carbon and the oxygen. I could easily have said, I'm going to draw this double bond between the chlorine and the carbon. Okay, or maybe with this chlorine and the carbon. And you can do that. Pretty much any 2 atoms that are connected to each other are typically fair game for drawing, for forming a double bond if they have lone pairs on them that you can get rid of. However, there is a third rule to drawing good Lewis structures that I kind of glossed over. Okay, and that is you want to minimize formal charges. Now, what are formal charges? We're not going to cover that here. That's something that I think I kind of gloss over in Chem 103 because I think it would take too long to explain. And most of the examples you see, it's not an issue, so we kind of just forget about it. For any of you who are going on to Chem 111 and 112, that is a concept that you do have to keep that rule in mind when you're drawing Lewis structures. So if any of you are curious about how formal charges work and how to use them, I'd be more than happy to explain that to you. Okay, just reach out to me and I'll or stop by my office hours and I'd be happy to explain that. Okay, but so in a nutshell, the reason that I chose to draw that double bond to the oxygen is that when I draw it that way, this oxygen winds up being neutral in terms of formal charges. Okay, um, basically, if I drawn a circle around this oxygen and sort of like counted each of these bonds by as half of their number of electrons, there are 6 electrons around that oxygen, which agrees with the number of valence electrons of an oxygen atom that's not bonding with anything. Okay, whereas if I'd done that with with the way I've drawn chlorine over here with only a single bond, this would be neutral, and if I'd put a double bond here, the chlorine would no longer have a neutral formal charge. Okay. Likewise, here with the oxygen likes having 2 bonds. If it has only 1 bond and 3 lone pairs, it would wind up having a negative formal charge. Okay, which isn't the end of the world, but like I said, it's typically nice to have neutral atoms as much as possible. Okay, and minimize formal charges. But again, don't stress too much about that. If you're this is a Chem 103 class, formal charges rarely come into play. So you actually probably wouldn't get a question like this, on a quiz or exam, or at least not without some extra information telling you like draw the double bond to the oxygen. Okay. So even though you could draw 3 Lewis structures for this, really it's only this one that's sort of most correct. Okay, so that being said, if you are going to draw the other 2 resin structures where there are double bonds between the carbon and the chlorine, as far as Chem 103 is concerned, I would mark that correct. If you were in Chem 111 or 112, I would, say that you ought to know better, but for Chem 103, I think that still counts as a valid Lewis structure. Okay, so I talked way too much about that third rule that we're not going to deal with. So are there polar bonds in this molecule? Yes, there's a difference in electronegativity between carbon and oxygen. Oxygen is very electronegative, carbon is not. That's a very polar bond. Likewise, chlorine is much more electronegative than carbon, so again, we've got a difference in electronegativity here, so these bonds are going to be polar. Okay. 3D model sketch. I've drawn this kind of T-shaped. To be honest with you, we'd want to draw, the proper way to draw this is to have these chlorides kind of pointing downwards here where we have a 120-degree bond angle. Okay. So it, basically, I guess I can draw it really quickly. In real life, if I were to have these electron pairs spaced out properly according to Vesper theory, your chlorines would be pointing downwards a little bit like this. So you have a trigonal planar molecule. 3 lone pairs over here. Okay, so that's kind of what that would look like in real life. Again, don't, if you're one of my students, don't stress about drawing it this way. I'm mostly looking at your Lewis structure to make sure you have the right number of electrons and everything's meeting the octet rule. Okay, what's the shape of this? Well, I mentioned earlier that if you had 2 atoms around your central atom, your options are either linear if there's no lone pairs, and if there is a lone pair, 1 or 2 lone pairs, it's going to be bent. What if you have 3 atoms around your central atom? Okay, so if we have 3 atoms, okay, then our options are going to be, if you have no lone pairs around your central atom, those 3 atoms are going to be spread out as much as they can, right? And what happens is they basically form what's called a trigonal planar molecule. In other words, those 3 surrounding atoms are going to spread out into form a triangle, hence the name trigonal, and they're going to be in the same plane as the central atom. The whole thing's going to be flat, okay? And that is what we have here. This is going to be trigonal planar. just going to brave as trig plan, but trigonal planar is the name of this shape. Okay, so these three atoms are on the outside are forming a triangle, and this whole molecule is flat. That's why it's trigonal planar. Okay, now if you had a lone pair on that central atom, that lone pair would push those three atoms downward, and it would make what's called a trigonal planar shape. A trigonal pyramidal shape. Okay, so it still starts with trigonal, but it's pyramidal. Okay, that lone pair is going to push those three surrounding atoms downwards to make sort of the legs of your pyramid. Okay, so that's the key thing to realize. If you have three atoms around your central atom, you know the name's going to be trigonal something. All right, those three atoms are going to form a triangle. If there's no lone pairs, the molecule is going to be flat or planar. If there is a lone pair, it's going to make a pyramid shape. Okay, so that's trigonal planar. Now, ask yourselves, is this molecule polar or not? Okay, so if I look at that central atom and I look at what's attached to it, do I have everything coming off of it as the same? Well, I have a chlorine, I have not a chlorine. Okay, so oxygen is different from the chlorines, so this is going to be a polar molecule. Okay, I have a chlorine half to the molecule and I have an oxygen half to the molecule. Okay, and that's what makes this polar. All right. Let's try an example of something that has a charge. Let's try this nitrite ion over here. Okay, what do you do if you have a polyatomic ion that has a charge assigned to it? Well, the charge only really affects the total number of valence electrons. So basically, it's going to just affect your calculation over here. Other than that, the rest of this is all pretty much the same. Like, you're going to go through the same process for all the other questions. Okay, so for example, now we have a so here we have nitrogen, right? That's in group 15, so that's 5 valence electrons for that. Okay, we have 2 oxygens, so let's put that in parentheses, 2, and oxygen's in group 16, so it has 6 valence electrons. Okay, so each oxygen has 6 valence electrons, but there are 2 of them, so keep that in mind. Now, if your molecule were neutral, you'd just stop there and you'd add up these numbers. But what do we do with that -1 charge? Well, the negative sign tells us that we have an extra electron. So this is a little counterintuitive, but if you have a negative sign here, if this is a -1, you have to add 1 electron for it. Okay? Likewise, if you have a positive charge, as you can see in this next one, a positive charge means you're missing an electron. Because again, remember, electrons are negatively charged. Okay, so an extra 1 gives you that negative charge, which is why we have to add it. A positive charge means you're missing 1, so you've got to subtract, 1 number from your total. Okay. Please note in both these examples, the magnitude of this is 1, right? -1 plus 1. It's possible to have things that have charges that are, more than 1. So, for example, like actually, let's see if there are any examples down here. Yeah. So, for example, our carbonate ion over here has a -2 charge. So here I would add 2 electrons to my total. Okay. Anyway, so in this case, I have 5 electrons from my nitrogen, 6 electrons from each of my oxygens, so 12 total, and I have an extra charge, an extra electron that's giving us that -1 charge. So when I add this up, I get the conveniently even number. Let's see, 12 plus 6 is 18, so I should have 18 electrons in my diagram. Okay, when I'm done with it. All right. Again, please note we have an even number of electrons. If you did this math and you got an odd number, that would have told you made a mistake somewhere. Okay. All right. So let's draw this out. We have the nitrogen listed first, so that's going to go in the middle. Okay. And we're going to draw 2 oxygens attached to it. So I'll just draw it, kind of, again, like my sort of bent method. Again, if you draw it kind of linear, that's totally fine. Okay. So yeah, let's give everything its octet rule. So this oxygen has 2 electrons from this bond. let's give it 3 lone pairs. So it has 8 electrons. Oops, sorry, I should probably. There we go. I think it made that a little bit easier to see. Okay, so 2, 4, 6, 8. That oxygen's happy. Let's do the same thing with this oxygen. It's got 2 electrons in that bond. 4, 6, 8. Okay, so 2, 4, 6, 8. That oxygen's happy. Now let's tackle that nitrogen. 2, 4, 6, 8. All right, there we go. So we now have 8 electrons and around our nitrogen. But let's add up the total number of electrons shown in this whole diagram and make sure we've done this correctly. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Ooh, we've got 20 electrons. That's not 18. So we've got 2 electrons too many, which means we need to form a double bond here somewhere. Now, the double bond has to be between the nitrogen and one of the oxygens. Those are the only 2 things that are connected to each other. We can't draw a bond between the 2 oxygens because, well, they don't have a bond between them to begin with. So let's pick one of the oxygens and our nitrogen. So let's say we pick this oxygen over here. I'm going to get rid of a lone pair on that oxygen. I'm going to get rid of a lone pair on the nitrogen, and I'm going to draw an extra bond between those 2 atoms that I just erased lone pairs from. So again, notice that my oxygen still has 2, 4, 6, 8 electrons. My nitrogen has 2, 4, 6, 8 electrons around it. Again, that's a good thing. But if we add the total number of electrons for this diagram, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, and that's the number of electrons we need. So we're all set here. Okay, so now that brings up the next question: where is the negative charge on this molecule? If we had covered if we had covered formal charges, you would know that this oxygen is neutral, and this oxygen is going to have a -1 charge, and so that's actually where that negative charge is housed over here. The nitrogen, by the way, is also neutral in this example. Okay, but since we're not covering formal charges, let's keep things simple and just say, all right, somewhere in this molecule there is a negative charge. So I'm going to put square brackets around the whole thing and just put the negative sign on the outside so that, we've acknowledged that there's a negative charge in there somewhere. Okay? All right. But now that brings up the question, could we have a resonance structure for this? And the answer is yes. Remember, I just arbitrarily chose to draw this double bond between the nitrogen and this oxygen? Well, I could have easily just chosen to draw it down here between the nitrogen and this oxygen. So if you have space, feel free to draw that. So I could just draw it, in other words, have my double bond between this oxygen, and have a single bond between this oxygen. And of course, this will still have 3 lone pairs because I wouldn't have erased any from here. This will have only 1 lone pair, and this one will have only 2 lone pairs. Whoops. There we go. And again, this still has a negative charge. So you could draw your 2 resonance structures that way. Sometimes to show that these are in resonance, we oftentimes draw a double-headed arrow between the 2 of them to show that they, they're basically, both these structures are in resonance. They both represent what our Lewis structure should look like. Okay. That being said, again, if you don't want to draw both of these, or you don't have room to, if you can just say somewhere here that there are 2 resonance structures, you just put the number 2 somewhere, so that I'm aware when I'm grading this that you know that there's a second resonance structure out there. That's sufficient for me. You can draw just one of these 2 and just write the number 2 somewhere over there, or write 2 resonance structures, so I know that you're aware of it. Okay. Any polar bonds in the molecule. Now, nitrogen and oxygen are both pretty electronegative, but there is an electronegativity difference. So I would say that these nitrogen-oxygen bonds are going to be polar covalent bonds. Okay. Yeah, pretty much the only time you have bonds that are non-polar are when they're essentially the same element, because then you know that the electronegativity value for those two atoms are going to be the same. Okay. Again, now for our 3D model sketch, this will be a bent molecule as I've drawn it, with that lone pair kind of pushing them downward. So if you want to see that in 3D, I scroll up here. That's kind of what this bent molecule look like. Again, as I pointed out, if you have two atoms coming off your central atom, it's either going to be linear or bent. It's linear if there's no lone pairs on there, and these two atoms want to get as far away from each other as possible. But as soon as you have a lone pair in there, that lone pair is going to push on those two atoms, bending the molecule. And that is the case over here. All right, that lone pair on our nitrogen is pushing those two oxygens closer to each other, and it's bending the molecule. Now, that bond angle is going to also be roughly 120 degrees, because we have three things coming off that central atom. It's kind of like our trigonal planar shape here, where, again, just swap out one of these atoms for a lone pair, and you've got kind of the essential shape that we're seeing here. Okay, so again, if you want to draw that fancy, you can draw that out here. So you can show the two lone pairs there, three lone pairs in this guy. And again, this is just one of the resonance structures, but that's what that looks like. Again, if you have room to draw this and you want to, feel free to. But since this is still going to be essentially flat, a 3D model sketch isn't really telling us too much. Okay, so I'm mostly again looking to see that have you drawn this Lewis structure correctly? Does it have the right number of electrons? Are the atoms meeting the octet rule? Okay, do you recognize how many resonance structures this could have formed even if you only drew one of these two resonance structures? Those are things I'm looking for. Okay, your ability to draw something in 3D isn't as important to me. All right, so next up, is this molecule polar or not? Okay, short answer, if it's got a charge, it's going to be polar. But let's look at the shape here and determine if that's going to happen. So we have our nitrogen, okay, in the middle. We have an oxygen coming off of it and an oxygen coming off of it. So far that's looking like that might be nonpolar. However, don't forget that lone pair. That lone pair is different from the oxygens that's attached to that nitrogen. And so we have kind of a lone pair half to this molecule and an oxygen half of this molecule. And therefore, this is a polar molecule. It has different sides to it, making it polar like a magnet. Okay, they're just as you have a north and a south pole on a magnet, you have a lone pair side and an oxygen side on this, polar molecule. All right, so I think that should hopefully be enough examples to get you the concepts that you need to finish this worksheet. Again, check with your instructor if you need to do all of these questions. They might have you only do select problems. Likewise, there's a page that's kind of intentionally blank. If your instructor has a few ideas for molecules that they really want you to draw, because I think they'd be good examples of what you're trying to cover, your instructor might tell you to use this page and to fill in the formula of whatever molecule you're drawing. Okay, but that being said, if you're one of my students, I'm just gonna leave this page blank. Okay, yeah, and that's basically it for this lab.